Hello, I'm Brian Young, and today we're doing 26104, Electrical Theory. Let's get started. 26104, Electric Theory. After successful completion of this module, you should be able to calculate values in resistive circuits, identify the resistance in series, parallel, and in series parallel circuits. Apply Ohm's law and Kirchhoff's laws to various types of circuits. Use Ohm's law to solve for unknown circuit values, explain Kirchhoff's current and voltage laws, and apply Ohm's and Kirchhoff's laws to solve for unknown circuit values. To install safe and reliable electrical systems, you must understand electrical circuits. In this module, you'll review how to calculate equivalent resistance values and apply Ohm's law to series, parallel, and series parallel circuits. You'll also learn about Kirchhoff's voltage and current laws. One point zero resistive circuits. The objectives of this module are to calculate values in resistive circuits, identify resistance in series, parallel, and series parallel circuits. A resistance is an electrical property that opposes the flow of current through a circuit. It's measured in ohms. Resistance is calculated in different ways depending on whether it's a series, parallel, or series parallel circuit. In this section, you'll learn how to identify resistive circuits and solve for unknown resistances. 1.1.0, identifying resistances in series. Now here's the highlight. It says a series circuit has only one path for current to flow. This means that the current flowing through R1 is the same as the current flowing through R2 and R3. It's also the same current supplied by the battery. Here's an example of a series circuit. Let me zoom out just a little. Here's a circuit. Here's the battery. So the current is leaving the negative and it's going through R1, R2, and R3. And it's the same amount of current. However much current is flowing in the circuit. If it's 2 amps, there are 2 amps flowing through R1. There are 2 amps flowing through R2. There are 2 amps flowing through R3. A series circuit is a circuit that only has one path for current to flow. It says you can find unknown values in a series circuit using any variation of Ohm's law or the power equations. Here's a review of the 3 forms of Ohm's law. So they've got E equals I times R, I equals E divided by R, and R equals E divided by I. And as a review, E is the voltage, electromotive force, I is the current, the intensity, and R is the resistance, measured in ohms. So the voltage equals the current times the resistance, the current equals the voltage divided by the resistance, and the resistance equals the voltage divided by the current. The power formulas are P equals I times E, E equals P divided by I, and I equals P divided by E. So power measured in watts equals the current times the voltage. The voltage equals the power measured in watts divided by the current. And the current equals the power measured in watts divided by the volts. Here's a highlight. It says the total resistance of a series circuit equals the sum of all the resistances in that circuit. So RT equals R1 plus R2 plus R3 plus Rn. That N stands for the number of resistors in that series circuit. So if there are 3, it's R1 plus R2 plus R3. And if there's 12, it's R1 plus R2 plus R3 plus R4, bop, 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 till you get to R number 12. The N stands for the number of resistors in that circuit. The circuit shown in figure 2 has a 50 ohm, a 75 ohm, and a 100 ohm resistor. Find the total resistance in the circuit, add the values of the three resistors in series. So they're asking us, what's the total resistance in the circuit? Well, 50 plus 75 is 125, plus 100 is 100, 225, excuse me, 225. So the total is 225 ohms. And there's their example right there. 1.2.0, identifying resistances in parallel. A circuit that contains two or more paths for which current can flow is called a parallel circuit. Most practical circuits are wired in parallel, such as the low voltage lights shown in figure 3. Most all of the circuits we run are going to be parallel. If you have receptacles in a house and they're all on the same circuit, all of those receptacles will be wired in parallel to assure that every receptacle has 120 volts. In parallel, the voltages are all the same. Same with lighting. It says there are three methods of calculating resistance in a parallel circuit. These are the reciprocal method, the product over sum method, and the method for equal resistances only. So 1.2.1, using the reciprocal formula. This one looks like it's the most difficult to do, but it's actually the easiest, I find. And you can use it for any number of resistances in parallel. If you have two resistors in parallel, or three resistors in parallel, or four resistors in parallel, you can use this reciprocal formula. The product over sum can only be used with two resistances. You can do multiple resistors in parallel using the product over sum, but you're going to have to do that formula more than one time. If you have three resistors in parallel, you'd have to do product over sum with two of them and take the result and use that with the third resistor, doing the product over sum method again. So with the reciprocal method, you only have to do it once. Here's the reciprocal method. Reciprocal formula is the total resistance equals 1 over R1 plus 1 over R2 plus 1 over R3. So they have three resistors in parallel. They have a 4 ohm, and a 5 ohm, and a 20 ohm resistor in parallel. So on your calculator, you just use the reciprocal button. Here it is right here. It's 1 over x. 1 over x is the reciprocal button. Or you might have a calculator that says x to the negative 1 power, and that's also reciprocal. So on this example, we would say 4 reciprocal plus 5 reciprocal plus 20 reciprocal equals, now we have to reciprocate one last time. If you look, the formula is 1 over R1 plus 1 over R2 plus 1 over R3. So when you get done doing all three resistances in parallel, you have to reciprocate your answer one last time. And it says the total resistance in this circuit with a 4 ohm, a 5 ohm, and a 20 ohm resistor in parallel is 2 ohms. Remember that in parallel, the total resistance is always going to be less than the least resistor in parallel. In this case, the least resistor in parallel was 4 ohms. The total resistance is 2 ohms. It's less than the least resistor in parallel. So let's take a look at their example. Example number 1 says, find the total resistance of the 2 ohm, 4 ohm, and 8 ohm resistor in parallel as shown in figure 5. So here's figure 5. We have 3 resistors in parallel. We have a 2 ohm, a 4 ohm, and an 8 ohm resistor in parallel. So in order to find the total resistance of this circuit, we'll use our calculator. And we'll say 2 reciprocal. Now, reciprocal, just as a refresher, is when you flip a fraction over. If I had 2/3 and I reciprocated it, I would put the 3 on the top and the 2 on the bottom, and I would have 3 halves. If I have 1/4 and I reciprocate it, I'll have 4 divided by 1, 4 over 1, which is 4. So the reciprocal of 2 is 1/2, and the reciprocal of 4 is 1/4. The reciprocal of 1/8, of 8 is 1/8. So let's start again. We'll say 2 reciprocal is 0.5 plus 4 reciprocal plus 8 reciprocal equals. Now, remember, we have to reciprocate it one last time. We have 0.875, but we're going to reciprocate one last time. And we get 1.142 as our total resistance in this circuit. Okay. All right. Let's see what they got. They're saying the reciprocal of 1 over 2 plus 1 over 4 plus 1 over 8. And they put down their answers as 0.5, 0.25, and 0.125. So that's the same as what we got. And they have 1 over 0.875 ohms. And when you reciprocate one last time, you end up with approximately 1.14 ohms of total resistance in that circuit. When resistances are connected in parallel, the total resistance is always less than the smallest individual resistance. In this example, the total resistance, 1.14 ohms, is less than the smallest resistor, which was 2 ohms. And it goes on to say, suppose you add a fourth parallel resistor of 2 ohms in the circuit. How does this affect the total resistance? Well, so now we have a 2 ohm, a 4 ohm, an 8 ohm, and another 2 ohm resistor. So let's use our calculator and see what happens to the total. We say 2 reciprocal plus 4 reciprocal plus 8 reciprocal plus another 2 ohm resistor reciprocal equals, it's 1.375. We have to reciprocate one last time. So it took the total from 1.14 and brought it down to 0.7272. We can round up to 0.73 ohms of total resistance. And that's what they got, 0.73 ohms. The effect of adding another resistance in parallel is a reduction of the total resistance from 1.14 to 0.73. The reason for this is that we have added another path for current to flow, thus reducing the overall circuit resistance. 1.2.2, using the product over sum formula. You can use this formula to find the total resistance when there are only 2 resistors in parallel. So the total resistance equals R1 times R2, that's the product, over R1 plus R2, that's the sum. That's why they call it the product over sum method. The 2 values multiplied together divided by the 2 values added together. Figure 6 shows how to find the total resistance of a 6 ohm resistor and an 18 ohm resistor in parallel. In this case, the total resistance is 4.5 ohms. So we have a 6 ohm and an 18 ohm. They multiplied 6 times 18, and they got 108. They divided it by 6 plus 18, which is 24. So their total is 4.5 ohms. And again, the total resistance is less than the least resistor in parallel. So example number 1, they say, find the total resistance of a 5 ohm and a 10 ohm resistor in parallel. So 5 times 10 equals 50, divided by 5 plus 10, which is 15, and 50 divided by 15 is 3.33. Example number 2. What do you think would happen if we increased each of the resistances in the previous example tenfold? Let's find out. Find the total resistance of 50 ohms and 100 ohms in parallel. So 50 times 100 is 5,000, and 50 plus 100 is 150, and the total is 33.33 ohms. So basically, when we multiplied them by 10, the answer is also multiplied by 10. Using the formula for equal resistances in parallel. This is one of the easier ones. I don't know if it's the easiest. If you have multiple resistors and they're all of the same value, you can divide the value of one of those resistors by the number of resistors. So in this example, they say there are two 200 ohm resistors in parallel, and the equivalent of one 100 ohm resistor. So you take 200 ohm resistors divided by two of them, the total is 100. If I had four 100 ohm resistors in parallel, I would do 100 ohms divided by 4 equals 25 ohms. Here they're doing two 100 ohm resistors in parallel, and 100 ohms divided by 2 is 50. But if we, the two 50 ohm resistors are the equivalent of one 25 ohm resistor. Oh, I see. They have this figure 7, the equal resistances in parallel. They have two 200 ohm resistors, a 100 ohm resistor, and a 50 ohm resistor, and they're asking us what is the total resistance? Well, the two 200 ohm resistors are equivalent to a 100 ohm resistor. So now we have two 100 ohm resistors in parallel, and the equivalent of those two is 50 ohms. Now we're left with two 50 ohm resistors in parallel, and the total is 25 ohms. So anytime you have two resistors in parallel or multiple resistors of the same value, you can divide that value by the number of resistors in parallel, and it'll give you the total ohmic value. 1.3.0, working with series parallel circuits. This can be a little bit confusing, but understand that you have rules for series circuits and you have rules for parallel circuits. And when you're talking about the part of the series parallel circuit that are series connected, you're going to use the series rules. Those rules being the current is the same everywhere in a series circuit, and the resistances are additive, and the voltage drops are additive. In a parallel circuit, the voltage is the same everywhere in the circuit, the currents are additive, and the resistance is the reciprocal method. So 1.3.1, recognizing series and parallel combinations. How do you recognize which part of a circuit are series connected and which parts are parallel connected? This can be obvious on a drawing if the circuit is simple. However, you may have to redraw more complex circuits into a form that is easier to recognize. So here's a series circuit. It has 3 resistors in series. Here's a parallel circuit with 3 resistors in parallel. Here's a combination circuit that has a series resistor and 2 parallel resistors. So in order to solve this, you'd have to solve the parallel resistors first and get an equivalent resistance of those 2 parallel resistors. Then you would add them to the value of the series resistor, because that series resistor is in series with these 2 parallel resistors. So here's what they say. They say start with the negative terminal of the power source and trace the path of current flow through the circuit and back to the positive terminal of the power source. If the current does not divide anywhere, it's a series circuit. If the current does divide into separate branches, but there are no series loads, it's a parallel circuit. If the current divides into separate branches, but there are also series loads, it is a series parallel circuit. Figure 9 shows resistors connected series parallel circuit, and the same circuit is redrawn in a simpler form. redrawn version makes it more obvious that R1 and R3 are connected in series, while R2, 4, and 5 are connected in parallel. So here's a series parallel circuit. R1 is in series with the rest of the circuit, as is R3. It's in series with the rest of the circuit. R2 is in parallel, but it's in parallel with both R4 and R5, which are in series. We know this because when we trace the current through R4, there's nowhere for it to go but through R5. So R4 and 5 are in series. To solve this circuit, we'll have to add R4 and 5 together and get an equivalent resistor. Then that equivalent resistance is in parallel with R2. We'll solve them by using the parallel rules. When we're finished finding the equivalent resistance of those three resistors, then we can add R1, R245, and R3 to get the total resistance. Okay. Here they say they've redrawn the circuit to make it a little bit easier to understand. So R1 is in series, and R2 is in parallel with R4 and 5, which are in series. And R3 is in series with the rest of the circuit. 1.3.2, reducing series parallel circuits. Most of the time, all you know about a series parallel circuit is the applied voltage and the values of the individual resistances. To find the total resistance, you must reduce the circuit to its simplest form. This means applying the rules for series and parallel circuits to combine the values of the resistors into a single equivalent value. Figure 10 shows how to reduce a series parallel circuit. In the circuit, resistors R2 and R3 are connected in parallel. Resistor R1 is in series with both the battery and the parallel combination of R2 and R3. Use the formula for equal resistances in parallel to find the resistances of R2 and R3 combined. So R2 is 20 ohms, R3 is 20 ohms. So if we take 20 ohms and divide by 2, we'll find that the equivalent resistance of this parallel branch is 10 ohms. Now we can add that 10 ohms to the 5 ohm resistor R1, and the total resistance of this circuit is 15 ohms. That's what they found here. They said 20 divided by 2 equals 10, and then 10 plus 5 equals 15. Well, if we wanted to find the total current, we could say 30 volts divided by 15 ohms, and we find that the total circuit current is 2 amps. So there are 2 amps flowing through R1. So there's 10 volts dropped across R1, and the other 20 volts is dropped across Rs2 and 3. Let's see what that looks like on the smart board. We have 5 and 20 and 20. Okay. I'm going to turn the page here, and let's redraw this circuit. We have, oops, wrong color, excuse me. Let me get my color here. So we have a battery, and that battery came to resistor R1. And then there were 2. I'm going to draw it a little bit differently than they did. I'm going to make it more obvious that we have 2 parallel resistors, R2 and R3. I'll draw the nodes and then go back to the source. And they said that this is a 30 volt source. And they said R1 is 5 ohms. And they said that R2 is 20 ohms. And R3 is 20 ohms. So right away we're going to combine R2 and R3 by taking 20 ohms and dividing it by 2. So the equivalent resistance is 10 ohms. And I'm going to use a different color. I'm going to use orange as my equivalent resistance. And here's an equivalent resistor that is 10 ohms. So now I'm going to redraw my circuit to make it a little easier for me to understand what's going on here. There. Here's my 5 ohm resistor R1, and here's my equivalent resistor R23, and it's 10 ohms. Remember, that's the equivalent resistance of R2 and R3. I'm going to call this R2, 3. This one is R1. So now we'll combine these two by adding them together because now they're in series. I'll extend my page. I'll put in my voltage value of 30 volts. And now I'll draw the final equivalent circuit. This final equivalent circuit has one resistor of 15 ohms. And this resistor is R1, 2, 3. So I have 30 volts impressed across 15 ohms of resistance. And if we use Ohm's law, we'll find that, I'll write it over here, I equals E divided by R. The current equals the voltage divided by the resistance. So 30 volts divided by 15 ohms equals 2 amps. Excuse me, I didn't put my V in. Equals 2 amps. That's the total circuit current, 2 amps. IT equals 2 amps. So when I go back to this equivalent circuit, I have 2 amps flowing through R1, and I have 2 amps flowing through R23. Now I can find the voltage drop across R1. 5 ohms times 2 amps equals 10 volts dropped across R1. 10 ohms times 2 amps equals 20 volts dropped across R23. And that's important to know because when we go back to the original circuit, we'll know that we have 2 amps flowing through R1, and we had 10 volts dropped across R1. We have 20 volts dropped across R2, and 20 volts dropped across R3. So here, to find the current, 20 volts divided by 20 ohms equals 1 amp. And over here, 20 volts divided by 20 ohms equals 1 amp. So this 2 amps of current splits when it gets to this node, and 1 amp went through R2, and 1 amp went through R3. And then they combined, we had the same 2 amps going home back to the battery. Okay? That's how you would solve for voltage drops and current through the individual resistors in that circuit. Now, 1.0.0 section review. You can use Ohm's law to find the values of each branch current in a parallel circuit. True. Which of the following is true regarding a parallel circuit? Parallel circuit, it has more than one path for current to flow. That is true. Which of the following is true regarding a series parallel circuit? Well, if it were a series circuit, it would only have one path to flow, and the resistance is the same throughout all circuit components. No. Once reduced to an equivalent series circuit, the total resistance is found by adding the series loads. That is true. Current flow through each resistor is always less than half. No. C is the correct answer. Once reduced to an equivalent series circuit, the total resistance is found by adding the series loads together. Very good. Okay, we'll go on to